Okay, good morning everyone. So welcome to our seminar. So it's my pleasure to introduce Professor Chung from Department of Mathematics and Statistics at University of North Carolina at Greensboro. So Professor Chung obtained his PhD in mathematics from Indiana University in 2013. He's right now working on topological data analysis. It's kind of a new topic to me, but it's a very old topic to Hamid. So, I think the topic itself should be very fundamental to people working on big data or even sparse data. To know the shape of data is of fundamental importance. So, without further introducing, so let's welcome our speaker.
Thank you very much for the introduction, and thank you for coming, and thank you for inviting me to give a talk here. It's my pleasure to be here. So today I'm going to talk about what is the shape of the data, right? So this is purposely very vague, right? But the main topic is really introduction to computational topology and how this topology can help us analyze the data. That's really the main topic today. So I like to start with this little comic here, right? So fields by purity, right? So very often people think mathematician is the most pure subject in science, right? So you have physics, chemistry, I think engineer somehow lie in there, right? So usually mathematics is considered as the most abstract subject. Not to mention, even within mathematics, topology is one of the most abstract subject in mathematics, okay? So how does topology help us understand this really practical data, this big data? How do we use topology to analyze data? Okay? So a little bit about my background, see where I come from. So I studied mathematics throughout my whole life. I got my PhD in Indiana University, where I study fluid dynamics, partial differential equation, and some computational methods. And since then, I've been working on other two postdoc positions at Kansas and William Mary. Okay. And when I was in college in William Mary, my mentor Sarah Day, she introduced me this new field, computational topology. Right, so this is a really exciting field right now, and since then I have a really great time working with some other scientists from different fields. So today you are going to see 4 applications, right, fit in the interdisciplinary seminar. So we're going to see 4 applications. First, the type of eyes, we study the structure of the eyes. Sleep-awake classification, we try to study the sleeping signal. And we are going to study human red blood cell. How does topology help us understand the behavior of the human red blood cell? Texture classification, very fundamental problem in computer science. Okay. All right, so what is topology? Okay, what is topology? In some people may think, okay, topology may be just the network, what is the structure of the network. But in mathematics, what do I mean by topology? It is really something called the algebraic topology. So the idea of the Euler characteristic is something we have learned when we was child, right? This dated back to 100 years ago. When we have played this game, I don't know how to pronounce this, but this is a game you can play. You can put up a lot of different shapes. So it turns out if you calculate the number of vertices, right, number of that vertices minus the number of faces, minus number of edges plus number of faces, you're going to get a very special number. This is called the Euler characteristics. So for some very special type like this polygon here, this cube or this different polygon here, if you calculate those, you will find out the Euler characteristic is always equal to 2. Right? So that's a very magical number. It turns out that's a very first mathematical invariants they developed in 100 years ago to classify different shape of surface. Okay? The only way to break this number 2 is you're going to make something really, really odd. Right? You're going to make something non-convex. This is only work for the convex polygon. If you have a non-convex polygon, then you can get something other than 2. Okay? And this is one of the earliest very beautiful mathematical theory how to classify, for instance, the different shape of the surface. Okay. But here you can already see a very strange thing. The Mobile stripe and this Klein bottle, they are really not the same, but the Euler characteristics are the same. So that motivate later Eric Beatty, he introduced this idea called the Beatty number. Right? That's really the foundation of the algebraic topology. So what the idea is very simple. Now we want to calculate something called the case-dimensional hole. Beta 0, beta 1, beta 2. What I mean is if I have a beta 0 counts the connected component. Beta 1 counts the tunnels. Beta 2 counts the air pockets. So a typical example, connected component, just how many pieces of objects do you have? For instance, if I have 2 pens here on my hand, I have 2 pieces of pen, so my connected components are 2. My beta 0 will be 2. Beta 1, a typical example would be circle, like a rubber band, that's a circle. A typical example for beta 2 would be like a basketball, a ping pong ball, that's the thing, okay? So this is a very interesting, if you Google Nobel Prize in Physics 2016, the Nobel Prize, in order to explain what topology is to general audience, he brought the dinner roll and a donut, right? So he tried to argue dinner roll is fundamentally different than a donut. Because from topology point of view, this is one connected component. There is no hole whatsoever. But donut, the shape is very different because in the middle you have a hole there.
What makes you fatter too?
Exactly, yes. So those two are totally different objects from topological point of view. Okay, so what's behind the scene is something called the algebraic topology. So I'm not go very detailed into this because this is going to be have one semester of the rigorous class in mathematics. So if you're interested, I encourage you to take this class. Here, the main theory is called the homology theory. And so homology theory is really just a way to measure the shape of the object. For instance, if I have this coffee mug, the corresponding homology group, whatever that means, this is a group structure to describe this shape. Okay? And what is the Beatty number? The Beatty number will be the rank of this group. Right? That's the formal definition of a Beatty number. Okay, so that's about enough the math. Let's talk about something we can actually see. Right? So this is the computational homology. We want to build up the space by anything. That's why we have a complex. Right? So here, the space we are building up is called cubical complex. So everything is built up by pixels. So it's naturally we're looking at the image data. But this is not the only type of data we can work with, but this is the most intuitive one. So we start with the image data. So for instance, if I'm looking at this black and white image, how do I count the Beatty number? So keep in mind, black is my color, white is null. White is nothing is there, black is present. So look at this. How do we count the Beatty number? Well, I already gave you the answer. Answer is 320. One more thing. This is a two-dimensional object. So you're going to have a vector of Beatty number. Beta 0, beta 1. Okay? No way you can get beta 2 because in beta 2 you need to be sit in a three-dimensional space. So this is a two-dimensional object. You can only have beta 0 and beta 1. All right. So we have beta 0 equal to 3. That means you have 3 different connected components. Okay, so let's count. You have 1 here. Let me give you a hint. Can you tell me what the other 2s are?
Upper left.
Upper left. Okay. and everything else is connected in the middle. Right? So you have 3 connected components, and there are 20 one-dimensional hole. How do we see it? Well, this is a one-dimensional hole. The space enclosed by the black region, that's a one-dimensional hole. That's another one. This is another one. And then you can count. There are 20 of them. And this is Beatty number. For some math audience, this is actually coming from the Cahillio equation. This is solution of the Cahillio equation. There's some researchers are trying to study the behavior of the solution using the topology. Right? So you have this very complicated pattern. You can change back to this Beatty number, and you can study the pattern of the solution. And now, if I have a 3-dimensional data, if I ask you to count the Beatty number, homework problem, right? So this becomes infeasible to human. That's why we need computer. And thanks to the theory doesn't count the dimension. Theory works for any dimension, any general dimension. So if you have a 3-dimensional object, you throw in this machine, you will get this number, 1,000 one-dimensional hole, and there will be no air pockets. This is in instantaneous time. Computation is really fast. Okay? But at this point, we only show you binary image. Right? Binary image is not very popular, right? Because the actual data, a lot of time the data we receive is either color image or grayscale image or some different type of intensity values. Okay? That's why the theory of persistent homology comes in. Persistent homology comes in 2007, roughly around that time. It's a pure mathematics object. It's developed by Gunnar Carson. He's a professor at Stanford, and our friendly neighbor John Hare at Duke. So those two were the developer of the persistent homology. And since then, and later, maybe around 2013, 2011, around that time, people realized persistent homology is actually computable, and it's very fast. And people realize that, and then there are tons of application on how topology will help understand the different type of data. There are some material science data, some brain data, and some cross-media data, and fluid dynamics data. Okay. All right, so what exactly is persistent homology? Why is that very useful? In a way, you can think about persistent homology as a way to define Beatty number in a noisy setting or in a grayscale image if you want. Just think about as easy as possible. Suppose I have this image. I have this grayscale image. Our brain is so good at making pattern, right? So if I look at this, black, remember how black is the region, white is not there. If I look at this grayscale image, what do I see? If I want to count a Beatty number, I'm going to see there are 5 connected components and 8 one-dimensional hole. Right? You see this is 1, 2, 3, 4 in the background. So there are 5 connected components, and then there are 8 one-dimensional hole. Right? That is told by our human, by our brain. But how does computer know? Okay? So that's why it comes in the persistent homology. It's a very powerful tool. It can deal with the noisy data, or something like this. How do we define the Beatty number in this setting? So for instance, in this case, the way to do it is you can actually think about this grayscale image. I suppose everybody very familiar with the image. You can think about the grayscale image as the composition of the binary image. Right? This is called the threshold decomposition. You have 255 binary image consist of this grayscale image, right? So for each binary image, you will be able to compute the Beatty number. Okay? And more importantly, this relation is called a filtration relation. So each binary image is a subset of the other. So this creates this very nice subset relation. And that in mathematics is important because that gives you an induced homomorphism. What does that mean? That means you can not only calculate the Beatty number for each binary image, you can also connect the Beatty number from this binary image to this binary image to this binary. So you can track, record how the binary image, how the topological information is stored throughout the time. Right? That's what the persistent homology is all about. So let me give you a very simple example. Please don't be mad at me. This is extremely simple, but we'll show you the idea. Suppose I'm looking at 3x3 images. I'm looking at the threshold decomposition. So I'm going to get a 10 binary image. Okay? So when threshold equal to 1, you're going to see this block there. When threshold equal to 2, you see this, and then so on. Okay? So let's take a look. So when this is a binary image, right? So now when threshold number equal to 2, you have this thin worm, right? The first time you see that. And then when threshold number equal to 3, this connected component disappear because it joined with the other. So that one disappear. And you notice when threshold number equal to 3 to 9, this type of shape, this structure, I call circle, this circle persists for a long period of threshold. Okay? And that's how you can see this might be the robust feature in this image. This is actually what you see in your brain. This is actually a circle. Okay? So there is a way to store all this information. This is called persistent diagram. The way you do it is you put the birth value on the x-axis and you put the death value on the y-axis. What do I mean by the birth value? The birth value is the first time you see the structure, and the death value is the time when this feature is gone. That's what I mean by death coordinate, birth coordinate. So for instance, this feature you will be seeing at this point here, this triangle here, the birth at 2 and death at 3. And this feature here, born at 3 and die at 10. Okay? So that's typical persistent diagram, store all of this information. And notice this is a two-dimensional image. So you're going to have persistent diagram 0 and persistent diagram 1. That will give you two different information, connected component information and circle information. Okay, so let's take a look at this example again. If I calculate a persistent diagram of this image, I'm going to get, this is beta 0th level persistent diagram. This is the first level persistent diagram. Okay? Forget about everything. Let's just count the number here, if I count this. Remember before, what do I say? This thing generated, if this close to the diagonal, that seems like a noisy generator because look at this example. This is just intermediate step in order to get to this final stage. All right, so something along the diagonal seems like a noise to us, and something away from the diagonal that seems like a robust feature to this image. Okay, so if I simply look at the long life generator there, the things away from diagonal, if you count how many points are there, 1, 2, 3, 4, 5, that's exactly fits our intuition, 5 connected components. So there are 5 robust features. And if you count here, 1, 2, 3, 4, 5, 6, 7, 8, so there are 8 robust features, and that fits our intuition, 8. Okay? So the main topic today is we're going to play with the persistent diagram. And how do we make sense of the persistent diagram? This is one way to understand the persistent diagram. One typical way people know how to do it is just look at long life generator, right? And people tend to think the short life generator may not be so important. Okay? All right, so it turns out it is an extremely important, extremely challenging problem in TDA. TDA refers to topological data analysis. There has been a major push in our field trying to understand or trying to make sense of persistent diagram. So there have been persistent landscape. This is more likely the classic one. when I say classic, right? But this is really 2015. It's very new. Very classic one, persistent landscape, persistent images, and there are some kernel methods. You're trying to put the probability distribution on top of the persistent diagram, and there are some more machine learning type of technique called the code book, a backward word from the natural language processing, and there are some other different. So it is a major research area in this world, trying to understand a persistent diagram. Okay, so we propose, well, first we call it persistent statistics. Right? So very simple, very naive, but it works really well. So the idea here is I have a persistent diagram. I want to summarize by a single number. Can I find a single number to represent this persistent diagram? Okay, that's a simple idea called persistent statistics. So let's take a look at the first example, human red blood cell. This is joint work with Madalena at Harvard. So we have two different types of data. We have a new cell and we have the old cell. The main problem here is we want to understand the different behavior of the new cell and the old cell. Old cell means that cell newly formed, okay? Maybe just 1 week old or 2 weeks old, very newly formed. And the old cell means that cell is going to die very soon, maybe 5 months old. Typical lifespan of the human red blood cell is 6 months. Okay? So it's well known that new cell perform much better function-wise, much better than the old cell. Okay? So they were trying to understand why is that. Okay? So maybe fundamentally their shape or their behavior somehow is different. That's why we are trying to understand. Okay? So we have this image data. We have 13 new cell, 13 old cell. They're all from different adult donors. So this is a video data. For each cell, I'm going to have a 5,000 frame. Okay? So this, you are looking at some example of this. Okay? All right. So there are two big questions. First is called the roughness. So one type of researcher think new cell might be rougher, right? Just like our brain. Some studies suggest very smart people, their brain may be rougher, right? So similar idea. They think the new cell is rougher. Maybe you have more folding, something like that. Another one is called the complexity. Whatever that means, I will get to that. Okay. So first, the roughness. So in 2007, 2012, and there are some other work, they're trying to use the idea of the roughness. Okay? They came up with this classical roughness from material science, right? So the root mean square. So just looking at the intensity value and then calculate the root mean square. Right? If you have much more variance, that means the surface is rougher. That's the original.
It's also from electrical engineering. We use it actually in electrical engineering for signals.
Okay, yeah.
Root mean
Root
square.
mean square. Yeah. So this has been studied for like healthy cell and unhealthy cells. So people somehow study this. But if you look at this, this is really intensity value. If I think about extreme case, if I shuffle this pixel around, right, you're going to get the same root mean square, but the spatial pattern is totally different. Right? So here, topological information is global. So we're going to see some spatial information more. So the information will be more than just the intensity value. The second one is complexity. This group of people at Harvard, they have this very interesting hypothesis. Complexity is the sign of the health. In their earlier study, they discovered the healthy baby, if you monitor their heartbeat, versus an unhealthy baby. Right? So a healthy baby's heartbeat is very complex, very, very unpredictable. They are kids, right? Whereas the unhealthy baby, it's not complex at all. It's very regular. You can almost see it's like the sine curve. They're very regular. So that's the sign of thing they believe, healthy person or healthy organism is usually going to have some complex, some unpredictable factor there. Okay? So here we were trying to understand those two things. So can we answer some sort of roughness about the human cell, develop the topological roughness? And second, can we answer some sort of complexity? Maybe new cell is more complex than the old cell. So let's take a look. This is the persistent diagram we're looking at. Old cell and the new cell. That looks like this. Okay? The first thing we notice is if it simply counts the number of generators. Okay? So simple, but it gives you something. Okay? If you simply count the number of generators, what do I mean by generator? Just the blue point in this each diagram, right? Each point. You count number of points and then you plot this box plot, you're going to find new cell typically has less generator and old cell typically has more generator. Okay? If you think about this in one-dimensional case, this is a very simple idea. If you think about one-dimensional case, what does a generator refer to? If you have a one-dimensional function, how do you make a generator? Well, you're going to need a min-max pair. If you have one min-max pair, there will be corresponding generator. Right? So in order to create that, you need to have a min-max pair. So that means if you look at a new cell, if you think about this way, that means the new cell may have more up, down, right? It's more min-max pair, and the old cell may have less min-max pair. So maybe new cell is rougher in this way, and old cell is smoother in this way. Okay? But this is just very simple observation. Let's take a look deeper. All right. Trust me, if you look 7 hours longer, you will see the pattern. That's how powerful our human brain is. Let me tell you the answer, right? The pattern, it seems like the old cell, if you look at the location of the persistent diagram, it seems like the generator is all over the place. Okay? Whereas for the new cell, it seems like it's bottom heavy. It's bottom heavy. If I'm just looking at the shape of the persistent diagram. Okay, so I look at this histogram, B plus D over 2, that will tell you the location information. That does suggest that the new cell is bottom heavy and the old cell is all over the place. So we use the very fundamental statistical variability, coefficient of variance, skewness, and kurtosis. Okay, trying to understand the distribution of D plus B. Okay? And this is the work by my former colleague, Larry, and his buddy at Purdue. So they plot a lot. They plot a lot of the distribution, right, well-known distribution. They study CV, coefficient of variance, and skewness. You plot all the distribution on this plot, you can see this very beautiful region separated by different distribution. Okay? So thanks to his idea, we're trying to do a similar thing. So let me remind you what's going to happen. I have an image data. I calculate the persistent diagram of that image data, and then I only look at the location, the shape of the persistent diagram, and then I look at the distribution of this thing, and I calculate CV, SK, and KU. And this is the result we see. Okay? Blue dot is the new cell. Sorry, blue dot is the old cell. Red dot is the new cell. Okay? So what does that mean? That means, remember I have 13 different cells. Each cell has 5,000 frames. So there are 13 multiplied by 5,000 points. That's how many points here, and that's another 13 multiplied by 5,000 points. That's how many points here. And we can see there's a clear separation. Right? This suggests that maybe you can use one single frame. You will be able to distinguish between new and old. And also, maybe there is a continuum between the old cell, how this old cell migrate, so the other way around, how the new cell migrate to the old cell. Okay? And if you look at the skewness also confirms our intuition. If you look at the skewness is always positive for all of the new cell. What does that mean? That means new cell is positive skew. That means new cell is, bottom heavy. Okay? All right, if I look at the different plot, the skewness and kurtosis plot, and you don't see much separation. But here comes a really interesting one. Theoretically, there is a theory lower bound on kurtosis and skewness. This is k equal to x squared plus that. You can prove that. It's a very interesting proof, but you have a theoretical lower bound there. Okay? And there have been a study on
S being the skewness?
SK being skewness.
No, S squared. What's S?
S is skewness. Yes. Okay. So there have been a study on the relation between skewness and kurtosis. People find out there will be a quadratic relation in some complex dynamics. I think in here, this is, they observe this quadratic relation in stock market, and weather prediction problem, and in some fluid dynamics problem. So here we go. If we calculate the similar thing, if we calculate the coefficient between the xk squared and ku, you will find out the new cell is really highly correlated. It's almost 1 for every cell. That means it does follow the quadratic relation, whereas the old cell does not have that strong relation. Okay? So this may suggest the new cell may come from this complex dynamics or chaos dynamic. Okay, good. So let's move on to the next application. This application is sleep stages classification, and this is a joint work with Hao-Ting and Dr. Luo in Taiwan. He is a medical doctor in Taiwan. We have this very massive data. Subjects sit in the hospital and they have this ECG, try to monitor the patient's or the subject's ECG. And here is the typical, this is not ECG. So this is a problem, like sleep stages. There are 5 different sleep stages. You either awake or in rapid eye movement sleep stage, okay, also known as REM, and then a different stage. This is non-REM, non-REM2, non-REM3, and so on, okay? And specialist is trained to look at the signal, biological signal like this. This is you're looking at the instant heart rate signal, okay, for any subject or something on your watch. You can monitor your instant heart rate. Specialist is trained, or in hospital is trained to read this data, okay? Usually in 30 seconds, every 30 seconds, they will be able to label, okay, in this 30 seconds, I think this subject is in the awake stages, or is in REM stage, or is in non-REM stages, okay? So it's going to be annotated every 30 seconds by human. It's a specialist, okay? So here the problem here is, can we develop a way to study or to automate this whole process? Okay. So there are 3 different data we have. The one is a private data, and those 2 are public data. The 80 subjects and 27 subjects, and each subject has about 7 hours IHR. So here's the main task. The main task is this is really a first step, right? We just talked about 5 different stages, but we only care about sleep and awake. This is just the first stages to, much bigger projects. How do we classify sleep from awake? That's already a very challenging problem. For one, this is awake. The number of awake signal is only 14 versus the sleep signal is 700. It's much more. So it's a highly skewed problem. Okay? So this is like, if I'm really dumb, I look at this signal. If I guess every label is sleep, I will still get like 97% accuracy, right? That's huge, but it's.
Sorry, what's 14 versus 760?
The number of waking signals and the number of sleeping signals.
760 is asleep.
Yeah, so it's highly skewed, right? Right? So identifying the awake signal is much more important. Okay? So this is the method we do. Right? We have very straightforward. Okay? You do a sub-level set filtration, you can do the time delay reconstruction, and you compute the persistence diagram, and you compute the persistence statistics, and use the persistence statistics to do any machine learning type of algorithm. Okay? That's the pipeline. Very simple, very straightforward. So what do I mean by the persistence statistics, right? So in our work, motivated by this work, we studied the skin lesion, and motivated by the previous work, human red blood cell, we discovered that the distribution of the D plus D and D minus D contain a lot of information. If you don't know how to deal with persistence diagram, maybe you can start with those two distributions. That will tell you something. Okay? And there's another very interesting feature is called the persistent entropy. Right? This is developed by Professor Krim here. This is the persistent entropy is also a very important thing. So here we propose these 9 different features. Right? If you calculate the mean of this distribution and standard deviation, there's all this 9 indicator. Right? So it's very good for, almost can characterize the distribution of D plus D and this D minus D plus the persistent entropy. Okay, those features, it will allow us to do a very good job of classification. So here's the result. Before you look top, let's look at the bottom. Bottom is the state of art. This bottom one. The bottom one is last year work by Houghton and his group at Duke. They used state-of-art, the deep learning algorithm technique, try to classify sleep from awake. Okay? And remember what I just said, the identifying awake is much more important. So we will focus on the sensitivity. If you look at the sensitivity of their work, it's about 57%, 50%. Okay? Whereas we are doing topology, think about what do? I just extract a feature that's intrinsic from the signal, just the topological feature, and I just do support vector machine. Right? Nothing else, nothing less. And then the sensitivity we have is 70%, 70%, and 65%, 53%. Okay? Okay. All right, so the next topic I would like to show is how do we make sense of persistent diagram. Another way is you can make sense of this persistent diagram by mapping to a curve. Right? Mapping to a curve. So now you have a persistent diagram, you can map this to a functional representation. Okay? So this is a joint work with my half PhD students at Greensboro. The main task is to try to classify the different textures. So the database we're looking at is UIUC tag and KTH and the OutTag. Okay? Motivated by Euler characteristic curve. This is a very fundamental, very classic curve in random field. Right? Random field, this is a very nice book. You can take a look. Robert Alder, he also considered as the founder, yes, half founder of the persistent homology person. He has a very nice theory about the Euler characteristic curve and how that related to the random field and the important application to physics. Okay, so suppose you're looking at this grayscale image, whatever, you can calculate, just like I said, the threshold decomposition, and then you can calculate the Euler Beatty number, and you can calculate the Euler characteristic for each threshold, and you calculate for all possible thresholds, you got a curve. Okay? This does not require persistent homology at all. You can just do it from the homology point of view. You'll be able to do this. Okay? The Euler characteristic curve has been shown in other work. This is one of them. You can use that to do some classification. For instance, this is Michael, horse, dog, and cats. They use Euler characteristics. They will be able to tell the difference. Okay? So motivated by this, we developed a new family of summarizing the persistent diagram. because you can get Betti number from persistent diagram. This is one of the very basic information you can get from persistent diagram. Okay, if you just sum over the number within this set, just sum over the number in that set, and that's Betti number. But you can already see that if you just sum over that, you're not taking advantage of the information of the persistent diagram provide. Okay, and that's why we came in. We say, okay, now if you do this, if you generalize all this operation here, this is number, right? So number is the counting measure. If you can just sum over that, we simply generalize all possible way. You can generalize this, and you can also put some function on top of this set. And not only you can sum, you can also do average, you can also do min and max, whatever function you can come up with. So this is really a big family of framework how to summarize a persistent diagram. And we also have a stability result. Here are some examples I'd like to show you. Right? So if you put the function to be 1 and the operator to be sum, you recover the Betti number. And that's one natural way to do. Well, or you can put a function to be b minus d. So each generator you calculate b minus d, that's the lifespan of that generator, and you sum over that, and you got the lifespan curve. Or you can do the life entropy. This is the persistent entropy. They also have this a new way of summarizing function. It turns out that's really just recover their result over there. Okay, and the most striking thing is under this framework, persistent landscape is also one of our special case. Okay, so that's a really huge, because no one will think persistent landscape has something to do with the Betti number. Right? So now this new framework will be able to connect and bridge a lot of existing methods there. It gives you a very general framework. Okay? So here are the results. This is KTH, this is UIUC, this is LTAC. And what you see in here is you have different type of textures, and each different color represent that type of images. It seems like persistent curve is doing a really good job of classifying or representing the intrinsic characteristic of each different textures. Okay, cool. So we can look at their performance. Okay, so the bottom one are some TDA results, TDA methods. And this top one is the our results. Okay, so the model here is we simply, just like before, we simply calculate a persistent diagram and calculate a persistent curves, and then you do support vector machine. Okay, that's what we do there. A very simple pipeline. The first one is the Betti number curve. The second one is the lifespan curve. This is the multiplicative lifespan curve. And notice, it's very interesting, if you look at Euler characteristic or the Betti number curve, for the LTAC 0, you already get a really nice result, 97, 98% accuracy, okay, overall accuracy. I think in this data set, there are 10 classes or 24 different classes, and try to classify 24 different classes. Okay. The benchmark of LTAC is 99.5. I think they use the GABA filtering, trying to fine-tune the parameter and to get the 99.5%. Okay? And there are some other TDA technique. This one uses the kernel estimation, right? Trying to make sense of the persistent diagram by putting some probability measure on the persistent diagram. And there are some other work on the kernel method as well. And the most recent one was, I believe this one is the persistent path. They will be able to get 97 point. Okay? But the point here is, here we want to not only to compete is one thing, but here we really want to show topological feature is really, really important, and it's really good for the classification, can really represent something. Right? So here we don't do much work, we can get a really good result, 90-something%. Okay? And our result is fairly consistent throughout a different data set. So for instance, Altec 10 contains a different rotation. Okay? Different rotation. So if you're looking at the geometric method, you're going to use a totally different method. So in fact, this is rotation images. For the Altec benchmark, they had to use a totally different algorithm in order to get their benchmark. But for us, it's the same feature and same algorithm. It's a very consistent. The result is very consistent.
So what's the difference between the Altex and the KTH? I see that, for instance, that what you're proposing sort of drops in performance for KTH and UIUC.
Yeah, so UIUC
So
and
what's the
KTH.
difference between those data?
The image is
Yeah.
different, a little bit different.
Yeah, what's the difference?
What's the difference?
How do they differ? In what sense do they differ?
They're both textual.
They are all textuals, yes.
So what's the difference?
Very good. Good one. I think the differences are the way they collect the data, the way they take the pictures.
There must be something structural.
Yeah,
that's
maybe
different.
one is more homogeneous, another one is inhomogeneous.
Yeah, there's got to be something structural.
Yeah, maybe the UIC is more mixed.
I see. It's possible.
Yeah.
I don't. Very good. Yeah, I should take more into it, but
Yeah, I'm not familiar actually with these data sets. Yeah.
okay. Okay. The next topic is fern. Right. So this is the structure of the ice. So this type of ice only occurred in northern pole and the southern pole, Antarctica and Greenland. So what is the climatology? She is actually our collaborator, Caitlin. Okay. She goes to there and then collect the data. So here you're looking at the ice column. This is the ice column. On the top is the surface level. The people can stand there. On the very bottom level, you may not even see it, is the sea. But it's not sea, ice, very hard ice. Okay. So somewhere in the middle, very general, this is called fern. Okay. So intermediate step between the top level and the very bottom one. Okay. So what they are interested is, okay, so let's take a look at the example first. This is what the data we have. This is called the micro-CT data. This is a three-dimensional image. Yeah, three-dimensional image, but it looks like a movie, but it's really a three-dimensional image. Taken at a different depth. Okay. All right. So what is this problem? What is the main task here? Okay. So now if you think about a particle, if you think about yourself as particle, the top level, the surface level, there will be a much more space. If you are a gas particle, you will be able to move around on the top layer because there are so much space. It's softer, you can move around. And when you go deeper, you will find out you may be limited by some path. You may be able to go in this direction, but you may not be able to go that direction because of the densification. You go deeper, the ice become heavier and the ice become more compact. Okay? And if you go much deeper, you will find yourself some direction you will never get into that. All right? And also you may see some of your friend was trapped inside the ice. Okay? And that is the place they are really interested in because those air trapped inside the ice can be dated back to 1,000 years ago that contain a very valuable information about the, for instance, the components of the 1,000 years ago. Okay? But the big problem is no one really know the changes of the structure. How do you find you can look at the scale. The scale is 20 to 25 meter and 60 to 110 meter. The scale is really big. That is because this changes of the structure, no one has a really good understanding. Okay, so it's a poorly understood problem, and they are eagerly trying to understand how this Fern column changes in structure, right, in depth. Okay. And you can see this looks like a very natural way in topology, right? If you think about in the very bottom one, you will be able to see a lot of beta 2. They see a lot of the air pockets or a lot of different ping pong ball, for instance, right? So you can use topology, you can use Beatty number, you might be able to capture those things. Okay? So there are a lot of different problems we're trying to understand. We propose the topological way to do it, and we submitted the proposal to ARO. Okay, so the first problem we contribute, the first contribution we have is can you find a meaningful binary image? Okay, so what do I mean by a meaningful binary image? This binary image is going to be respecting the topological information of this. Okay. Why do I need the binary image? Well, because in their lab, what they do is they have this machine. Okay, they have this machine in order to calculate the volume, for instance, permeability, for instance, or how the water flows through that sort of parameter. They need a binary image in order to calculate those simple physics quantities. Okay? How do they find a binary image? Well, according to the machine, you can just select certain bottom and you will get the binary image. Okay? But it's very important because if you select the threshold somehow not good enough somehow, you may lose some topological information, and maybe that may give you a wrong information about the physics of this structure. So here we want to come in and give a topological way of how you can select in this threshold, and that threshold will respect the Beatty number of this object. Okay? So we come up with this automatic thresholding method that's based on the persistent diagram. Right? So this is my persistent diagram. And our idea here is trying to capture the robust feature. Right? So in the beginning of the lecture, we said the thing away from the diagonal might be the robust feature. So we want to capture the robust feature as possible. And this is a very interesting thing. This objective function we develop here is actually considered as a special case of persistent curve as well. Okay. Anyway, so we developed this automatic thresholding method based on we want to capture the robust feature and we want to avoid the noisy generator. Okay. And here is the result. Suppose we have, this is the persistent diagram for that three-dimensional image you just saw, and the threshold we choose according to the PD thresholding method is 121, I believe. And then not only you give a binary image, but also you will get the Beatty number as well. Okay, so their Beatty number is 4, 1, and 16. Okay, so here is one application. Okay. Here's one application we do. So suppose now I calculate, those are 7 meters, they are 17 meters, a different depth of the samples. If I calculate the persistent PD thresholding method, if I calculate the Beatty number for each slice. So now if I go back to myself, go to the two-dimensional case, you have 2D slices. If you calculate the persistent diagram according to PD thresholding method, the green one is the Beatty number respect to the number of the slices. The blue looks like 17 meters, and the red is 7 meters. So it looks like they are on a different level here. Okay? And what's more interesting here is in the 17 meter, this guy, it seems like there is a huge jump from this point on. There's a huge changes of the Beatty number. Okay? So we contact our collaborator, Caitlin, and she's told us, yeah, that looks like a seasonal layer to her. She was able to look at the data because she personally collect the data. She knows what's going on there. She will be able to tell us, oh, that looks like a seasonal layer. So yeah, the topology, we are not crazy. We might be able to capture some important property they are looking for. Okay? All right, so with that, I will stop here, and thank you very much for your attention. I talk a lot, and thank you very much.
Any questions? So can we apply homology diagrams to text?
Text, yes.
Yeah. So
The
so you
natural
showed how
language.
to construct the diagram for image data.
Yeah.
But how about the text data? Like how to construct those diagrams?
Yes, that's a very good point. So here we see a lot of images data, but actually the original of the persistent homology is work for the point cloud data. It's more like, let me see. It's more like this. You have a point cloud data, you can construct the persistent homology. Or if you have a network structure, you can do the persistent homology. For the text, I believe there are person in medicine. They first vectorize the text. And once you can vectorize the text, you will be able to apply the persistent homology. If you can have the point cloud data, if you can, in some matrix space, then you will be able to apply that.
I have a question in terms of when you build up your curve across scale. Have you looked at the stability of that? Because it seems to me that
Yeah, we have.
in the sense, okay, I didn't quite get that because you went through it. Stability in what sense? Because there may be different means of stability. You can inject noise. So there are ways of.
Yeah.
You know,
So the
interpreting.
stability result here means your small changes in your underlying function. Underlying function. Stable measurement persistent curve is. Yeah, if you have a small perturbation on your underlying objects, then the outcome of the persistent curve is also small changes.
What about the thresholding? In other words, as you build up your scale.
Yeah, it's all there. It's all there. So here we have. So there are two things. The first one, we develop the general bound, right? So you can develop the general bound, and then if you further assume this function is nice enough, this function is stable, then the persistent curve itself will be stable. So for instance,
Okay, so it depends on the functions.
yeah, like this one, the lifespan is known to be a stable measurement, right? So if you use that function as a persistent curve, then that persistent curve will be a stable measurement under small perturbation, and the curve will also give you a small perturbation.
Okay, thank you.
Yeah.
It seems that value curves describes a global feature of your data. Is there any application of local topological features on real data set?
Local, the only thing I can come, that's a very good question. So here are two ways you can take a look. The first, topology is a global thing, right? If you calculate the local information of that object, and there's no way you can combine them. That makes sense. So for instance, if you have images, right, you can calculate this. You can look at this portion of the image and calculate the Betti number. You can look at this portion of the image and calculate the Betti number. So in mathematics, there's no way you can somehow combine them and then tell me what is the information of those. Okay, but still, you can still use the local information maybe to be used as a classifier or something. Okay, so one thing we use is in the sleep stages analysis. Yeah, not there. Yeah, in the sleep analysis, what we do, we have this signal, right? So what we do here is we look at, very good point, we look at small chunk, and we calculate the Beatty number of those small chunk, and we use that as a feature to do classification. But that's a very good question. You might be able to use a local feature to do classification.
Any other questions? Okay, so if no further question, let's thank our speaker again.
It's very good.
Yeah.
Very good work.